Okay, so in review question 9, looking at a question that is referring to thermal expansion. So the context is that engineers in Seattle determined that a steel bar of length L would expand by an amount delta L when the temperature changes by 10 degrees Fahrenheit. And engineers in Dublin, Ireland are examining a steel bar of length 2L. How much will the steel bar in Ireland expand by if it undergoes a temperature change of 2.78 degrees? So the question is definitely examining the concept of linear expansion, but also sort of challenging proportional reasoning, mathematical skills, and setting up of sort of a system of equations. So sort of I wrote this equation a little earlier, so that delta L, so this is the key concept, that the change in length of a material is equal to alpha, the coefficient of linear expansion, times its initial length, sorry, it looks a little confusing, it's L times L subscript I, times the change in temperature. And this change in temperature should technically be change in temperature either in Kelvin, but a change in temperature in Kelvin is equal to a change in temperature in Celsius. But we have a challenging problem here with Fahrenheit, but we'll get to that in a second. Just sort of to note is that a delta T in Kelvin is equal to a delta T in degrees Celsius. So they have this, a change of 1 Kelvin is equivalent to a change of 1 degree Celsius. That's not true for Fahrenheit to Celsius or Fahrenheit to Kelvin. So what do we have here? So if we consider the Seattle situation, we know that the delta L in Seattle is equal to alpha. The alpha will be correspond to steel. So they're both measured. I'm going to assume that it's the same steel in both places. Times the initial length in Seattle is L, times the change in 10 degrees Fahrenheit, which I explain again. I wouldn't do this for a quantitative question, but it'll make sense in a second. And that's equal to delta L. And the delta L of Dublin will be equal to alpha, same alpha, but it's got a length of 2L. It undergoes a change of 2.78 degrees. So what's common here, and that's going to be equal to some value of this delta L. So what's common here between the two is the alpha. But what we have, the differences between the two is the temperature change. So how do we know, and this is again, what's very important here, this is a change in temperature and not a single temperature, so it's a delta. So you don't want to be converting 10 degrees Fahrenheit to Celsius or 2.78 degrees to Fahrenheit. It's a delta that's super important here. So I'll write down in shorthand what the equation that you need. So and I'll sort of maybe I'll do a derivation over here. But the key thing is that the delta T in degrees Fahrenheit is 9/5 of the delta T in degrees Celsius. So this is the same factor. So if you're interested in where this comes from, let's think about how we do single conversions. And I'll maybe just use this space over here so it's not, I won't muddle up the answer. So the T in degrees Fahrenheit is equal to 9/5 of the T in degrees Celsius plus 32. So that's how we will convert a single temperature in Celsius to a temperature in Fahrenheit. So 0 degrees Celsius is 32 Fahrenheit, freezing point. But a delta T in degrees Fahrenheit, of course, is T final in Fahrenheit minus T initial in Fahrenheit. So I'll put this on one line. So I'm looking at the delta. So what is the TF in degrees Fahrenheit? Well, that would be 9/5 of T final in degrees Celsius plus 32 for all that one. For instance, this would all represent, T final in Fahrenheit minus again 9/5 of T initial in degrees Celsius plus 32. We'll put all that in parentheses. And this would be T initial. So we have plus 32 minus times plus 3, that would cancel. So this would all give us 9/5 of T, oh, I'm messing this up, so sorry, 9/5 of T final in degrees Celsius minus 9/5 of T initial in degrees Celsius. Well, that's just 9/5 of delta T in Celsius. And that's what I'm trying to prove over here. And that would, then you can flip that the delta T in degrees Celsius would be 5/5 of the change in temperature of delta T in Fahrenheit. So you can reverse this if you want to. So in this question, you can treat it from the Fahrenheit side, or you can treat it from the Celsius side. You should get the same answer. So let's figure out, in a sense, how do we get these into a single unit. Okay, so let's try to figure out what is the change in temperature Fahrenheit that corresponds to a 2.78 degree change in degrees Celsius. So the delta T in degrees Fahrenheit, 9/5 of a 2.78 degree change in Celsius is 5 degrees Fahrenheit. So a 2.78 degree change is equivalent to a 5 degree change measured on the Fahrenheit scale. And this is, now we can see sort of there's a factor of 2 here, or a factor of 1/2 in the temperature changes, and that makes things convenient. And you can do the flip of that also if you want to work from the degree side. So what's common here is the alpha. So I'm going to write the alpha here in terms of delta L and the L and the 10 degrees Fahrenheit. So I'm going to write alpha, and this in a different color, using the first equation. So alpha will be equal to delta L over L times 10 degrees Fahrenheit in the first equation. And I'm going to substitute that into the equation for the delta L in Dublin. So delta L in Dublin is the alpha. Again, the alpha is common between the two because it refers to steel. Delta L is how it's defined here in the question, over L times 10 degrees Fahrenheit. And I'm multiplying all of that times 2L times the 2.78 degree change we just figured out is 5 degrees Fahrenheit. And this makes calculations nice and easy, so we can cancel out those L's. And then we've got 2 times 5 degrees Fahrenheit is 10 degrees Fahrenheit, divided by 10 degrees Fahrenheit, so that sort of all cancels out. And we just end up with the same change in the length. So choice D is the correct answer. So this, in a sense, you can sort of work through the answers that I've sort of chosen these two temperatures, so they're nice to work with, and then figuring out again the factors of there's sort of a factor of 1/2 or 2 in the temperature, there's a factor of 1/2 or 2 in the lengths, so we end up with the same change in length in both locations.